Okay. All right, so let's get started. So today we have a little bit of vocabulary to get through. This is just certain things we want to be able to say about subsets in Rn, and this vocabulary will sort of stay with us for the remainder of the course. We'll talk about it in the context of differentiation, partial derivatives, things of that sort, and then when we do integration, we'll need this vocabulary then as well. So let's get started on that. That's not going to be too bad. There's a lot of good pictures. So vocab. Well, we had this notion of an open ball and a closed ball. So let's recall and give ourselves some notation. So let's suppose we have a point. I don't know, P, let's call it P. And I'll give it coordinates A. And I'm going to be in Rn, but of course you should feel comfortable doing this definition in 2 dimensions or 3 dimensions if that's more your taste. So this symbol here means it's an element, so it's a point in this set of points in n-dimensional space. Okay, just a point. So then we have an open ball of radius delta. This is delta. This is also delta. This is lowercase. This is capital. So there's maybe some notation to remember. So an open ball of radius delta. This is centered at P. This is just this set. Well, I'll call it B sub P of delta. So this point down here is the center point, and then this is the radius. And it's going to equal just all of the points in n-dimensional space with these coordinates so that the distance is less than delta. Distance to P is less than delta. Okay. This is the distant formula in n dimensions. It's just a generalization of that in 1, 2, and 3 dimensions that we've seen. So this is less than delta. Now, so this is the open ball. If we want the closed ball, same idea. We can take this whole setup, just duplicate it, and we'll put a bar to denote closed here. And then we just make this not a strict inequality, but just an inequality less than or equal to. So that means you're going to be able to include the sphere at the boundary on the closed ball. So we have words for these things in different dimensions, in the lower dimensions that are different, right? So for in dimension n equaling 1, then we don't, what do we call an open ball? Or a closed ball? What do we call it? Huh? A line segment, I think interval, right? And it's an open interval. It's just an open interval. And a closed ball is a closed interval. So it's something, like P minus delta. Well, I'm sorry, I'll say A1 and A1 plus delta. Just that interval centered at the point at the number A1. So something very familiar you see in calculus. And then in n equaling 2, we'll say that, we call an open ball a disk or an open disk. I believe the notation in the book, it uses D instead of B to denote disk. And I won't, but it's just a rewrite of this definition. Okay. And then once you get to 3 and above, you just use the little ball. So these are sort of the fundamental little sets that we can work with and start defining other things in terms of them. So one of the things we want to do today, the first thing on the list here, is to define an open set. Let's call it S in Rn. This is just a set for which every element, say P in S, has an open ball centered at it. At P, which is contained in S. Okay. So what's the picture here? So the picture is, let's say we're in 2 dimensions and we have some set like this, and we drill out a few holes here or something like that. So the region is everything in here. Okay, and then so why do we know this is open? Well, I did this dotted line on the boundary here, and that denotes that I don't actually include the boundary. So if I take any point in this set, right? If I take any point, then I can take a disk centered at that point, and I might have to make that disk small, but if I make it small enough, I can, hopefully. Okay, well, let's see. If I make it small enough, I can put it inside of this region, right? The entire disk will fit inside that region. That's the idea. Now, of course, as you get really close to the boundary, your disk radius has to get really, really small. But the point is there's no point on the boundary. If you had a point on the boundary, any disk you made would have to overlap something outside of the region. So it would not be an open set. That's the idea of an open set. So this is open. Okay. So what's a closed set? So a closed set, this is easy, in Rn, is the complement of an open set. It doesn't mean that it's like really good friends with an open set and it says nice things to it. People know what the complement is of a set. It's just all of the points not in the set. So it means if we take our set and we look at everything not in it, it's open. So this is the notion of a closed set. So what are some closed sets? So this guy is an example of an open set. What are closed sets? Well, you could take something like this. That's closed, right? A curve with its endpoints. Because in the complement is open. You're just kind of taking a scissors and cutting out a little region, and everything will have a disk in the complement. So, and also, of course, you can take regions that include their boundary. That should be closed. These are closed. And I don't want you to get the wrong impression. I mean, sets aren't either open or closed. They're sort of special sets that are one or the other. Now, you might be like, I'm not interested in abstract math. Why are you teaching me this vocabulary? Well, what you are interested in, though, is practical problems. And some theorems in mathematics aren't true unless you have certain conditions. So some theorems in mathematics are only true for certain types of sets, certain types of domains. And so if we don't have the language to express what that means, then we can oftentimes be running down, and trying to solve a problem that may not have a solution. So this is the reason we kind of developed this vocabulary, so we can say things kind of sensibly. Okay, good. So we have Open sets, closed sets. What about a bounded set? So this is a pretty simple notion as well. So we have these kind of, a bounded set is a set that doesn't sort of move off to infinity, where we're kind of staying within a certain kind of finite area, a finite volume or something. And this is a set. So the precise way of saying this is a set contained in some ball. Some ball. You can just take your pick, any ball. But of course, it has finite radius. Oops, P delta. It could be open or closed. It's some ball. Okay. All right. So these are some fundamental things that when you have both closed and bounded, these things work really well together. This is a notion called compact in math. And there's a place where you can often extremize functions. And so that's a nice feature to have, but we'll get to that a bit later. So now what I want to say is give this definition of this connected and disconnected set. This is what you think it is. So a set is disconnected if it is contained in the disjoint, I'll define disconnected, in the disjoint union of two open subsets. All right. Disjoint union means it's the union, but the two open subsets involved don't overlap at all. So this is what you think it is. You know, if I have a curve here and then I have a blob here, right? Well, I can take two open subsets that don't overlap, and they're contained in them. So this, I can disconnect these two sets. So this is a natural notion of disconnected. And of course, a connected set is a set in which is not disconnected. That's all. So set, connected set is not disconnected. Okay. Okay, great. One last term that I want to define, and then we'll move on to limits. And that's the boundary of a set. So the boundary, we'll give our set a name. Well, I don't know if we really need it, of a set is the collection of the sets. So yeah, the collection of points for which every open, or closed really, ball containing that point intersects the set, sorry, that should be an S, the set and its complement. So in other words, if we take a set like this, let's say we go like this, and then we sort of wrap it up here, and we consider all the points in here. Okay, I can choose some point on this set. And the boundary is what you would think it is. It's if I choose a point here, and I take a small, disk, it's going to both overlap the region that we're talking about and points that are not in that region. And it doesn't matter how small that radius of that disk is, it's always going to intersect both. So that's a good boundary point. So indeed, the boundary in this case would consist of, all of these points, but also all of these points because they both share that property. So you get all the points on what you think of as the boundary. But this gives you a mathematical way of a precise way of talking about what you mean. Okay, great. So this is all vocabulary. And as I said, we may not use all of it today, but we'll be encountering it in statements and theorems as we go. So at some point we have to get it in our brain. Okay. So right now what I want to do though is return to limit. And as I've tried to stress in lecture, the limits in higher dimensions for multivariable functions in particular become more unruly, I'll say, than in one dimension. So let's recall this definition I gave really quickly. I won't belabor it, but I want to draw a picture to see if you can't understand. See if you can understand. Hopefully you can. So let's suppose we have a function, and we'll say we have n variable function. And now I'm going to use some of the language I've just developed. So let's say this is a function on an open set. Open domain. So domain is sometimes regarded as an open or a closed set, but I'll just say open set in Rn. And we'll have some point, so I'll use this, give coordinates C. So P is C1, Cn. So we say limit as x1 through xn, the coordinates approaches, we could say P here, but let me say C1, Cn of f of x through xn equals L. And again, this is this delta epsilon if for all positive epsilon, there is a delta, positive delta, such that, I'm going to draw a picture in a second, so hopefully this will help, such that for all x in a small ball, sorry. So this is the equation for the ball, for the ball centered at P, x1 minus c1 squared, the inequality, I shouldn't say the equation, xn minus cn squared, less than delta, and greater than 0. We have the absolute value of f of x, 1 through xn minus L is less than epsilon. Okay, that's a very, very wordy definition. There's another way of kind of viewing this, but it's a little bit different. But let me give you the picture, which is, I think, how you want to think of this. So let's say we have this function, f, and let me draw just kind of some kind of function. Okay, so let's say we have a function f, and it's going to be defined over some range, some blob downstairs. So I'm going to draw a picture downstairs of the domain that it's defined on. And this is the graph of f. So this picture I'm drawing is the graph of f, pardon me. And now I want to find the limit of a particular point. So I take a point P in this domain. Here's my P. And I want to claim
that my limit is going to be what, I would expect, right? It's okay. That's all right. So I go up, what I expect is here, that the limit will actually be this value. Now, what do I mean that value? What I mean is that you take that, you take the height there. I want to say the limit of the function will be that particular height. Now, of course, you all have seen pictures in one variable where you have discontinuity and where you don't get limits, where you get these big jumps. So this picture looks pretty nice and smooth, so you would expect there not to be a big jump. So you'd expect limit to indeed be what you think it is. So what is this epsilon and delta? Well, what you have here is as I said, what you want to do is what you're guessing is that this height here is going to be your L, is going to be your limit. So that's your L. Now, what is this equation here, or this inequality here saying? It's saying that the values of f for the points x1 through xn that you put in, they're a distance epsilon away, at most epsilon away from this height L. So this inequality here, you can look at as giving you a sort of band around your limit. And when you put that band in, you kind of can draw that band around your graph. So maybe the upper side here is even above the graph. But if you made the band smaller, then you would get like a little, maybe a little band here. Okay? And you want to say that there's some region, some little disk. It doesn't have to be big. You can make it as small as you want. And as small as you want is you can choose this delta as small as you want. But there's some little disk around here so that when you look at the values of all of the points in that disk, you land in that band, in that region. Right? So you land in here. Whoa. So everywhere in this disk will land you within this kind of interval region. And you can do it no matter how tight you make that band, right? No matter how small that epsilon is, this epsilon here, which would make it tighter and tighter around that value, you can always find a small enough disk that will land you. That's the idea behind this definition. It's a very deep, I would say it's a very difficult conceptual definition, but it's worth really trying to get your head around, I would say. Okay. So, of course, many of you may not be interested in the math here and may just be like, well, okay, what do we do with this? How can we use this? Well, of course, what we can do once we have these very rigorous definitions is we can start proving some statements, which I won't include proofs here, but I will include the statements that allow us then to evaluate limits, okay? In situations where we are faced with actually trying to calculate them. So the upshot of this definition is that we can legitimately say certain true things about limits. Okay. And in particular, all of our previous intuition with arithmetic, I'll say, is still holds in higher dimensions. So all of our arithmetic rules hold. And what do I mean by that? I'll say in dimension n. So what does all of them mean? What does that mean? So in particular, so examples. And that you look in the book, please, there's a lot of different, look in the online book. They list them, they give the exhaustive list. But some examples are, the sum of the limit is the limit of the sums, or the limits of two functions. Of course, all of this is when all limits exist. So put that into any of your statements here. So the sum of the limits is the limit of the sums. You can replace sum with products or same with products, difference, so on, difference, products. Quotients is fine, but you have to be careful that the denominator is not 0, right? That the limit of the denominator is not 0. You have to be careful with that. Quotients with an asterisk. Right. So some of these basic arithmetic rules hold, which means that we can manipulate limits in higher dimensions when we're dealing with familiar functions. Okay, when we're dealing with familiar functions where we don't see a denominator going to 0, that kind of thing. In particular, limits of polynomials, or I'll say limits of, they're called classical functions, polynomials, trigonometric functions. Let me not call them classical. Let's say, just say continuous functions, pardon me, because I don't think you may be familiar with that term. Okay, I'm going to retract this. I don't want to say this. Sorry, guys. This is okay. Well, I do want to keep this, and then I want to say one more thing, which is a very useful thing. So, also compositions work as before, work as in one variable. So, in particular, so i.e., that means in particular, layman terms, if, say, a limit of one function, I'll just do, say, one variable, g of t, as t approaches c equals L, and the limit as x, y, for example, approaches ab of f of x, y equals c, then you can compose them and you get what you would want. So then something like limit of g composed with f of xy as xy approaches ab, this is L. So this is an example of a composition of two things where you get what you expect. Okay, there is a lot of terminology, abstract notions, and so on that I'm putting in the notes here. I think at this point, what we should probably do is do some problems, right? And see something kind of concrete. So the first set of problems I want to do is, what are the techniques you can use to show a limit does exist, and how can you deal with it? So this is sort of the easier bit in higher dimensions, where you want to use these rules that I've just been talking about to try to actually get limits. So here's some problems. So find the following limits. And usually if you're on a test or some kind of exam or some problem set, homework, you'll see some statement if they exist. So let's do the first problem. Will be the limit as xy approaches, say, 1, 3 of x squared plus y squared minus sine of x minus 1 over cosine of pi times x. Something like this. Okay, so problem 1. Solution. So as I said, when you have like polynomials, so this here is a polynomial in two variables. The limit, this is a continuous function, so the limit really is obtained just by putting in the value. This sine is what's known as a classical function, it's a trigonometric function. it's continuous. You can just put in a value. Same with cosine. So the only thing with a problem like this that you have to watch out for, and this is something you should look for, is if you have a fraction, you're taking a limit, look in the denominator and see if you're approaching 0. So cosine here is approaching cosine of pi times 1 because x is approaching 1. And cosine of pi is -1. So that's not 0. So you're not in any trouble here. And so you just can substitute in this case. So here we can substitute and say that the limit is in fact the quotient of the limits and break everything up. And of course, you'll get 1. So this limit equals just 1 plus 9 minus sine of 0 is 0 over cosine of pi, as I said, was -1. Ours is -10. Okay. So the first thing you should check, and this is the first problem I'm doing with limits, always check, is this just a continuous function at this point? If it's a continuous function at that point, it's not a trick. It's just easy. So always do that. Always do the easy thing. Okay, so now what if we have something that's a little more difficult? So let's say we have the limit as xy approaches, I don't know, -1 of, say, x plus 1 squared plus y minus 1 squared times the natural log of the same thing. What do people think? What do people think? So I think we actually had a problem in lecture that's very close to this, right? So hopefully you saw when I copied it, this has this pattern. It's something, this function has something times the natural log of something, the same thing. Now, as x and y approach -1 and 1, we do have, this is a nice polynomial, so we can understand what this limits to. What does this limit to? 0, right? It goes to 0. So what we're getting in this, if we were just to try to substitute, like we did a second ago, we would get 0 times natural log of 0. But we of course know that natural log of 0 is not well defined. There's no such thing. So that's a problem. So, however, we did, as I was just saying, we did talk earlier in a previous lecture about this guy. Do you remember this? This, I think we used some kind of L'Hopital's rule. We saw this as limit as t approaching 0 to natural log of t over 1 over t. We took derivatives, the numerator and denominator. We get 1 over t over a -1 over t squared. And this is the limit as t approaches 0, -t, which is 0. So we saw that this function had a nice limit as t approached 0, but this is actually just a composition. This is a composition of this function with this function. So if I call this equal to g of t, if I call that equal g of t, the function in particular, then I take f of xy to equal x plus 1 squared plus y minus 1 squared, then what we're trying to do, and we want the limit as xy approaches -1, 1 of g of composed with f of xy. And we have above what I just wrote down, this particular example is a tool that allows us to evaluate this limit and kind of get rid of that multivariable nature here. Because we know the limit of f of xy as xy approaches -1, 1 is 0. And we know the limit as t approaches 0 of this g is 0. So using those two things, we can just say using compositions, we have that the limit is 0. It's the limit. Yeah. Okay, so we can use that. So another tool, so here are two tools that we have some basic arithmetic rules that we can use in many variables. We have compositions, that's a nice thing that we can use in many variables. There's also another theorem that we can use in many variables, which helps us quite a bit. And that's the squeeze theorem. So I'll give an example of one of these problems. So let's say we're looking at limit as xy approaches 0, 0. So as we're approaching the origin of the following function, x squared, y squared over x squared plus y squared. So what's the solution? Well, so this is actually, you're going to see, I guarantee you on the exam, exam 2, maybe even the final exam, you'll see these types of limits. These are the easiest limits to kind of test your understanding of multivariable limits, is having these are called rational functions, right? They have a polynomial on top and they have a polynomial on bottom. So these are kind of very easy to write down and, understand, they exhibit interesting behavior. In this particular case, one thing you can do is you can convert into polar coordinates. So we'll convert our function, just write it as in polar coordinates. And if we do that, we know, of course, we recall x equals r cosine of theta, y equals r sine theta. When we do that, we'll get that this limit here is in fact equal. Well, as we approach the origin, we're letting r approach 0. And theta is actually sort of free to vary. Theta can do what it wants, but we need theta actually to be independent. I mean, we need our limit to be independent of what theta does. But we can put in our change of variables, cosine theta squared, r squared sine squared theta. And in the denominator, we get r squared cosine squared theta plus r squared sine squared theta. Of course, pulling out the r squared from the denominator, we get just cosine squared plus sine squared, that's 1. So here we get limit as r approaches 0 of r to the 4th cosine squared, pardon me. Let me make it a little bigger. Cosine squared theta, sine squared theta. I just assembled the powers of r, and I've got an r squared down here. Of course, I can cancel here. There's no problem there. And when I cancel, I'll get a 2 here. So this is just equal to the limit of this. Now you can see that this function, as r approaches 0, is certainly approaching 0. However, what I said a moment ago really should be something you consider. This is really the limit as r approaches 0 with theta being whatever it wants to be. So theta can do whatever it wants. So what you want is you want to say that this is sort of independent, this limit is independent of what theta is. And for that, you do need this squeeze theorem. So the squeeze theorem says that if you can take the thing you're taking the limit of, in this case, this function, and you can trap it between two functions that you understand, where their limit goes, then you know where the limit of this function in between goes. So here we can say, for this particular case, r squared cosine squared theta sine squared theta. Well, cosine and sine squared are both between between -1 and 1. So this is going to be trapped between negative r squared and r squared. Yes. Okay, that's true. That's true. That's a good point. I was thinking more along the lines of other cases where you can consider other powers, but you're absolutely right. Since these are squared, you're right. These are non-negative. But cosine is between 0 and 1, and sine is between cosine is between -1 and 1, and so is sine. So in other cases, for example, if I put a cube here and just a first power here, you would want to use the one I just wrote down. But this is fine here. And so here you can squeeze, but now you have complete independence of theta of this function. There's no dependence on theta at all. And of course, 0, 0. So that means that we can indeed apply the squeeze theorem and say that the limit as r approaches 0 of 0, this is equal to 0. This is less than the limit of what we're after. Which is less than also the limit of r squared as r approaches 0. Okay. So this will tell us that whatever this is, it exists and it must be equal to 0. So this is one technique that we use in many variables as well. So this, and now, okay, so now that I've talked to you a little bit about how you can find limits, what about when the limit doesn't exist? Well, and for that, I want to recall, or ask you, so what goes wrong in one variable functions when the limit doesn't exist? Well, I'll just say say x approaches c of f of x does not exist. Everyone writes DNE, right? What goes wrong? I think generally speaking, there are 3 possible things that go wrong. So stroll down memory lane here. I mean, 3 types of things that can go wrong. Anyone suggest? So I give you a function in one variable. I say the limit doesn't exist. What do you think might have happened? Oscillation. Oh, wow. That's like the most complicated one, right? So you could have like f of x. That's true. And it fits my number 2, let's say. Say you go x equaling 0, x approaching 0 of, say, sine of 1 over x or something. And this, you have this kind of crazy picture here where you're just, sine is behaving very nicely and then it starts going nuts. So it's not approaching a single value. It's just kind of moving. As you approach 0, you're getting closer and closer to sort of all the values on it. Other things that go wrong? Sorry? Disconnection. Okay. So the disconnection, I want to say that this is the limit as x approaches 0 from, say, the right of a function is not equal to the limit as x approaches 0 from the left of the function, right? At one of these pictures, right? You see. And I think the third thing, an example, I mean, I'm writing examples in these 2 cases of something like this. You guys all see this. You can go to infinity or negative infinity or both, that kind of thing. And I don't know, sometimes people are fine writing, okay, well, the limit is infinity, but sometimes you'll say the limit doesn't exist. Something like that. So to infinity, plus or minus. These are the three things that go on, I think, the three main things that go on. Now, all of these things happen in higher dimensions. All of these things happen. So certainly you could, I can consider in higher dimensions, I could consider something like limit as x, y approaches 0 of 1 over x squared plus y squared. Sure, that will go to positive infinity as I approach the origin. I could have just replaced x here with x squared plus y squared, and I get crazy oscillation as well. But 3 is the real guy. 3 is the one that's like, oh no, wait a minute. What's going on? See, the thing about 3 is this. The thing about 3 is that. What is 3 saying? 3 says, okay, I'm on an interval. I've got this point, in this case 0, but if I'm saying C here, I guess I should have written C. I've got this point, and I want to know what happens as the limit approaches, or as x approaches C to my function. Here's the thing about one variable. There's 2 directions. To one dimension, you can go from the left, you can go from the right. That's it. That's all you can do, right? That's it. If those limits exist and they're equal, the limit of the function exists, right? That's good. Okay, but now you guys are all grown-ups-ish. So you don't restrict yourself to one dimension. That's child's play. Now you're in 2 dimensions. Now, how can I approach this point? A lot of different ways. Boy, a lot of ways. I can approach this, I've got this way, I've got this way, I've got this way. And you might say, oh, wait a minute. Okay, so you have a whole circle's worth of ways, right? You can approach from a circle's worth of ways. You guys agree? Wrong. Wrong. I can approach it. I don't have to do that. I don't have to do that. I don't have to travel in a straight line. I can go like this. I can go parabolically around, to it. I can go in a little spiral. I can have a cubic approach. I got a lot of ways I can approach that point. And the thing about it is, if I approach this in every single way linearly, i.e. through a ray, and I saw that the limit of my function that I was interested in existed through each of those linear approaches and it was equal, the limits may still not exist because I didn't try that parabolic approach and I didn't try another approach. This can go wrong with some functions that you can write down really easily. So things can go completely wrong in higher dimensions because of this different approach situation. So what you cannot do, and I say this every time I teach, and it's hard that I almost never get understanding here, what you cannot do is you cannot prove a limit of a function in many variables exists by taking different approaches. But what you can do is you can prove that a limit does not exist by seeing that the limit is different when you take different approaches. You can do that. So taking different approaches to a point will give you a negative answer if a limit doesn't exist sometimes. So here's a problem where I want you to think about it about 1 minute. Let's take the limit of xy, very similar to what I just wrote, but I'm not going to square the numerator. Okay, solution. Let's take 2 approaches. One approach, go along, so this is the point 0, 0. First approach, I'll go along the x-axis. I'll just go along the x-axis. I'll do it in blue. So here, x is x, y is 0. So then I get the limit as x approaches 0 of x times 0 over x squared plus 0 squared. But that's limit of 0, which is 0. Another approach, let's go along the line y equals x. Then I can look at that. I've got the limit. Here I'll just take x going to 0, but y is equal to x, so I get x times x squared plus x squared, which equals, limit as x approaches 0, of x squared over 2x squared, which equals limit of 1/2 as x approaches 0, that's 1/2. This is not equal to that. I get two different values from two different approaches, so the limit does not exist. This is a good way of showing limits don't exist when they don't. Okay, all right, guys, I'll see you next week. Have a good weekend.